Good afternoon, everyone. Welcome to the first of the UK Acoustics Network Early Career Group Talks. I am Nikhil, and today it's my job to take you to the interesting world of underwater acoustics, to highlight the differences between underwater acoustics and acoustics in the air, the challenges we face, some examples of how we work in underwater acoustics, either in commercial or in research domains, and finally, maybe inspire you to join us. Let's go ahead. Let me share my screen. Uh, there you go. So, um, you might have heard the statement that we know more about the surface of the moon or the surface of the Mars than our own oceans. As engineers, it's our objective to quantify those statements. For example, I would say we know more about the surface of the moon or the surface of the Mars at the resolutions we have on the surface of the moon and surface of the Mars of the ocean floor. Now, there are many reasons for that. The ocean is a very challenging environment. It's unforgiving. You have to have sensors that are robust, that can work with for larger battery lives in salty environment, harsh waves and wind, and marine fouling, biofouling, and so on and so forth. The cost is very expensive to deploy, retrieve, data process, and all that. So I always like to highlight the challenge using this picture. Now, this picture shows you the bathymetry profiles in the ocean or the depth of the ocean across the world. The brighter the color in this figure, the shallower, and the darker, it's the deeper, except for the land, of course. Now, you can immediately pick out several features. For example, the North Sea around the UK and the Northern Europe is relatively shallow, 40-50 meters deep. You have lots of islands in the Indian Ocean, the Southeast Asia, which is shallow again. Then we have the Ring of Fire and the deepest part of the ocean, the Mariana Trench, right next to Japan. Many Pacific islands, the Mid-Atlantic Ocean Ridge, and it immediately tells you the scale and the depths that we're operating. This is roughly, uh, you know, the Atlantic Ocean is roughly 1,500 to 2,000 meters deep. Again, polar acoustics or polar oceans are increasingly being used for many operations, and near the Arctic Circle, the depth of the water above the Arctic Circle is shallower. Antarctic waters are really deep again. Now, this tells you that if acoustic communication is happening underwater across channels, so let's say between Europe and USA for some reason, the sound signal travels through many water depths, shallow and deep. It also potentially encounters many types of seafloors. It could be muddy, sandy, rocky, gravelly. So you already are underwater acoustics is already a very interdisciplinary domain to start with. You have geology, you have the properties of the water, so you do have to take into account all of that. But there is a better way to highlight what I'm saying by using a video. Let's go ahead. So in this video, what there is an animation that shows how sperm whales hunt underwater using sound. Now, what I want to focus on is think as engineers and see what the sperm whale is doing. At what frequency is it sending the signals out? How regularly is it sending the signals out? And how does it change its repetition rate, etc. So let's go ahead and let's talk about it in a bit. So, what do you think? If you want to look at a sperm whale as an engineer working on a sonar source or an acoustic source for doing target detection or fish detection, it is doing extremely exciting few things. One, it's using a very short pulse, and then it's waiting for the reflection to come back. It's using its brain to process the signals on how strongly reflections come back, how delayed they are, and then changing its repetition rate. And obviously it does all this processing in its brain, but the sonar works in a very similar principles. We'll talk about this a bit more as we go ahead. uh, However, the question is, if we want to communicate across basin scales, why not use electromagnetic spectrum as engineers? True, however, underwater, the electromagnetism suffers very strong attenuation, as you can see, except for, let's say, blue or near near ultraviolet frequencies. All of the electromagnetic signals are lost in the very few wavelengths once they encounter the water, which means most of the frequencies that you observe in slightly deeper waters are blue. And in contrast, acoustic signals suffer very little attenuation. For example, at the audio frequency of 1 kilohertz, the if you send it underwater, it loses for absorption roughly zero point 0.1 dB every kilometer. Now that's very little signal loss to absorption, which means you can talk across basin scales, for example, across the Atlantic Ocean, without appreciable loss, which is what large marine mammals, which vocalize at hundreds of hertz or even 20 hertz, 30 hertz, have been using for millennia. Now, having said that, as in an engineering sense, acoustics in the underwater domain does spread across many fields. For example, you have the seafloor and imaging, you have the underwater gliders that sense the ocean in some sense, you have fish sonars, ice, and you also have the sources for ambient noise, for example, rain, wind, you have drilling rigs, etc., etc. So it is a very acoustically active domain, and the more shipping we have and more increased shipping we have in recent times, we are increasing that our level of the noise level floor all around the ocean. And underpinning all of this is the speed of sound profile. Now, if we are talking mostly at the ground level for aeroacoustics domain, we don't worry about the changes to the speed of sound. We just consider it roughly 340 meters per second, the speed of sound in air, and go ahead with it. However, because of the way the sound propagates underwater, we do have to consider the speed of sound, the variation of speed of sound with depth. And this speed of sound, because the top layer is exposed to sun a lot, and because of the ocean properties, it is strongly dependent on temperature and pressure. So the top layers are strongly dependent on temperature, for example, and deeper layers are influenced by the pressure of the water above your head, and which means you always have a minimum on the sound channel axis, roughly around 1000 meters water depth, where all the signals gets trapped around. And this defines the rho C characteristic of each layer. Assuming that the water is incompressible, as C changes, the density, the rho C changes, which means the sound refracts around the deep channel axis, as shown in the simulation here on the right. Now, if the depth of the seafloor changes, the propagation of the sound wave also changes. It encounters, it scatters, gets absorbed, and so on and so forth. So for studies like here, where people have strategically placed a sound source in the Heard Island near Antarctica and tried to record the signal across different parts of the ocean, Any slight changes in temperature could be observed by changes in these receival timings, for example. So this trace shows you the received signal, and each of these peak corresponds to the signal scattering at the sea surface or sea floor, and a combination or a multiples of that. Um, and any changes in this figures out any changes in temperature across the spot. So we already have a sensing tool for the last many years to sense the change in the temperature of the ocean across many, many hundreds and thousands of kilometers. Now, this long distance propagation requires modeling. So the propagation characteristics of the signal across the sea floor, across the sea surface, the shallow water, deep water characteristics, temperature changes, and so on. So, which means the frequencies of interest have also have to be highlighted. Now, because water is much denser than air, it can sustain frequencies up to megasonic hertz, up to roughly 1 megahertz, and even beyond, without suffering much loss. So on the right, we have some of the sources, both industrial and natural, that span across these frequencies. The interesting thing to observe is most of those are broadband. So unless you have a sonar, military sonar source, centered around particular frequency, say 5 kilohertz, all of the sources are broadband, which means there would be a lot of overlap between whatever the marine mammal vocalizes, either using for foraging or hunting, with a ship sound or a sonar or a seismic air gun, which are examples of industrial noise sources. Now, here is an example of sound recorded from um, not sound recorded from the Arctic Ocean. Now, the classification of this is sea cracking ice. So I just want, I'll not play the whole audio, I'll play it for a bit, and I want you to listen to it and try and figure out how complex this sound is compared to what we regularly hear every day. That might sound like some sort of animal, but it's sea ice actually, stretching and cracking under the pressure of the waves and so on and so forth. So it's very important to have a knowledge of all these ambient noise sources in the ocean. One thing I want to highlight is the reference acoustic pressure in underwater acoustics is 1 micropascal, which means the dB scale, everything is referenced to 1 micropascal, unlike 20 micropascal in the air domain. And look at the scale and the order of pressure amplitudes that are encountered in the underwater acoustics, roughly an order of 10 to the 16, which means the dB scale is also again very important. And some of these are actually really loud sounds, which might cause physical or psychological response to many creatures in the underwater domain. A bit of historical perspective, only to bring out why underwater acoustics is so important. Now, although Rayleigh first formulated the wave equation in 1877, wasn't until 1913 that an underwater acoustic electrical oscillator, that means it sends the signal and receives the echo, was used to detection of the icebergs. If you imagine you are in a very foggy environment in the North Sea or beyond, and you don't know where you're heading in 1913, these type of source receiver combinations were very vital so that you don't hit any icebergs, for example, in 1912 for the Titanic. Now, so around that time in World War I, for example, you have shown you piezoelectric transducers were developed, and these were used for mostly detecting underwater submarines. And between the world wars, the focus was on more oil and gas industry, non-military use. And in the World War, again, it turned to submarine warfare, the SOFAR channel, which is where you have the minimum, and cavitation and avoidance of those cavitations so that you don't make any sound in the ocean when you move. And now we have interest in shallow water acoustics, marine mammal protection, acoustic communication, for example, GPS in the ocean, shipping noises, etc. Which brings us to this exciting figure here, which people in the underwater acoustic domain refer to as the Venn curves. What this Venn curve tells you is the lowest possible sound level across different frequencies you encounter in decibels with reference to 1 micropascals. That's the lowest level you would ever record because of the ambient prevailing sustaining noises. But you also have overlays with different sea states. The sea state is corresponds to the wave height. So the harsher the sea, the more loud it is in the ocean. And you also have levels that compare to shipping, different shipping activity, and so on and so forth. This figure can be used with the figure on the left, where you have the noise level again in decibels, roughly, and compared with the vocalization of different marine mammals. So, for example, if you have a sonar source or a seismic airgun array, it's broadband across many frequencies, and it is very loud, roughly 220 dB, 230 dB with reference to 1 micropascal, and it envelopes many of the frequency ranges of the marine mammals, which implies that they either suffer physical trauma due to the loud levels that they encounter or their bodies, or other psychological trauma or masking and those sort of things, which are of great interest nowadays. For example, this is an audio of a marine mammal vocalizing at the same time as a ship passing by. By the time the ship comes by, you barely hear the marine mammal vocalizing anymore. Now, following on the same vein as the previous picture, I would want to highlight the levels of the sound that we refer to in underwater acoustics as the source level, which is the hypothetical level of sound signal that you can potentially measure at a distance of 1 meter from it. And as you can see, along with additional information on the right that you can look at, many of these signals are very frequent. For example, air guns are really frequently used by oil and gas industry. Research sonars, these are all very loud, 195 dB, compared to the previous slide where you have the noise levels roughly at 40, 50, 60, 80 dB. You have a huge signal to noise ratio to do many things, but also may cause impact. So what sort of interdisciplinary studies that we can do in the ocean acoustics? These studies or these fields would have to be interactive and have to provide enough information across that we can't get from one study. For example, oceanography in itself is truly interdisciplinary in the sense that you can deploy sensors, you can measure the pressure wave propagating across these multiple sensors, use tomography to study change in temperature or change in the rainfall over a period of time. Um, it also includes many applications such as in defense, for example, anti-submarine warfare. You have target detection, you have submarine detection, fish detection, you have studies in climate change that figure out changes in temperature, changes in the sea dissolved CO2 content, for example. And most important nowadays is marine mammal protection and impact assessment. So I would like to split that into two regions generally, which is taken from Howe et al., which is active acoustics and passive acoustics. Active acoustics is you send sound intentionally for a particular purpose, listen to the reflections, and understand and process them and analyze them. Whereas passive acoustics is just deploying hydrophones underwater and other sorts of sensors, just listening and figuring out the information about the nature, about the anthropogenic characteristics and biological characteristics. We can expand them, for example, based on AUV missions, unmanned surface vessels, temperature, biology, for example, tsunami, ice warnings, rain, marine mammals. You have many fields that are influenced by underwater acoustics. So out of these, I would like to choose 3 examples to talk to you today. Uh, so 4 examples actually. So one is shipping noise. The other is 3 examples that we have worked either with universities or with the commercial partners or general operations every day. So on the left, we have an animation of sound levels recorded on the northeast coast of USA, and each of the dots correspond to one of the ships. And remember, the dB scale is reference to 1 micropascal. And you can see as each ship passes by, it does radiate a loud level of noise across the paths. And CFAS, the Center for Fisheries in East Anglia, have recently done this in the UK, and they've generated a figure that corresponds to this. So in this figure, you have shipping noise all around the UK, excluding all other noises. And the levels that we have recorded, the highest levels that they have recorded in some of the regions, were comparable to the noise that we hear from motorways, which is striking because these areas are very active, both for fisheries and marine mammals, but also for different operations, say, wind farm installations and so on and so forth. There is a huge focus on marine mammals, and for a reason. These mammals have been tuned to vocalize for many, many millennia. However, we've only first detected them in 1950s. For example, on the left, we have dolphin clicks. And you can really see the squeaking or the whistling noises in the spectrogram below. In addition, you also have funky sounds such as dwarf minke whales, which are known to produce Star Wars type vocalizations. So the other thing is we can get lots of information from satellites. And this information includes the cover of ice, the variations in the gravity, surface temperature, and so on and so forth. And because um, currently um, the the ice cover in the Arctic Ocean is gradually dropping, which means the shipping lanes are opening up in Alaska and other territories beyond the Arctic Circle. And as the ice level reduces, more oil and gas industries are interested in getting licenses for extracting oil and gas using seismic operations. These are again very active marine mammal regions. And any further loss of ice would increase industrial activity to such levels that uh, we have to seriously start recording levels in this, start publishing reports, and start figuring out the impact assessment in these regions. So I jumped the gun there a couple of seconds ago, but I do want to focus on three commercial examples, which would be exciting. The first one is measurement of levels from a big, large oil and gas asset using marine robotics, which we've done with BP. The second one is analysis of impulsive noise sources to extract environmental information. This is a research project that we've done with University of Bath. And the third one is industrial noise, our daily bread and butter, the thing we do for, generally commercially for impact assessment. So let's start with the first one. So here we have a modern sixth generation mobile offshore drilling unit. What this is basically is a huge vessel kind of device which can position itself at anywhere in the ocean. And once it positions itself, it starts drilling down for oil and gas. And it has four large propellers, and you can see the scale from here. And the idea is to deploy a 5-meter unmanned surface vessel with hydrophones stowed behind it, underwater microphones or hydrophones stowed behind it, to record and analyze the sound radiation characteristics of this mobile offshore drilling unit. Although studies have been carried out for structures like this in the far field, we weren't allowed to record any sound levels in the near field, which is roughly within the 500-meter exclusion zone of each of these megastructures. That's because of safety concerns. But with these kind of remotely steerable, controllable, unmanned surface vessel, what we were allowed to do is to go into this 500-meter exclusion zone along with our hydrophones and record sound level all around 360 degrees and also in the far field. Now for comparison, we also use drift buoys, which is we drop the buoys down and they float away, recording the sound at the same time. And the objective is to record the near field, record the far field, predict the levels to distances where we cannot record, and also estimate the source level, roughly what the sound levels would be like at the hypothetical 1 meter distance. Now, some of the results here, and as expected, and because of the very low frequencies radiated by these huge impellers, roughly below 125 hertz, 200 hertz, the sound level does not drop appreciably as you move away from the source if you follow the median line in this box and whisker plots. Of course, there are outliers, and there was a simultaneous operations software that was developed to remove any unwanted noise from passing by ships or other known signals. So looking at this figure, there is a slight drop in the levels in the near field, but overall it's pretty consistent. You can also extract information using GPS data and plot figures like this. For example, on the right, you have all these close passes and sound levels with reference to again 1 micropascal. And you can see sound levels slightly higher here on the northeast corner, which is probably because there was a propeller here active at the time of operation, and up to 5 kilometers. This gives you a spatial coverage of the signal of exactly the mobile unit, of the drilling unit. Now, what we did was we did measure the levels. We used a propagation model to estimate the signal up to much larger distances than the measuring distances. We could only measure up to roughly 5 kilometers, but we've extrapolated the signal using propagation modeling up to 100 kilometers and estimated the source level. So for example, we have all these all these dots are the measurement of sound level in that frequency band for 1 second. And then we run the modeling curves and use best fit analysis to estimate what the level would look like at different distances. And we do this for all frequencies, for all least square best fit measures, and we report the levels of the signal. Now, what these data would do is serve as benchmark for studies that come up and talk about these type of sources and compare them with different models. So second example, we've been doing this work with University of Bath for quite some time now. The objective is a presence of a seismic air gun. An air gun releases large amount of pressurized air into the water, as very similar to a click, a loud sound. The objective is to look at reflections from the sea floor and sea surface and the buried sediments. However, we can also deploy recorders that are not related to these hydrophones, which are mostly low frequency. We could deploy hydrophones that operate at higher frequencies, extract the information at higher frequencies and use that to sense the environment. For example, this is a typical signal of roughly 190 dB zero to peak signal. And this black curve is the signal and the red line is the noise floor across different frequencies. Now we can again run propagation models and figure out how the signals arrive at the receiver, and probably it encounters a target in the middle, and extract information about the B, which is the information about the seabed that is included in the acoustic signal. So for that, we ran both a shallow water and a deep water acoustic propagation model. And we shot rays, acoustic rays, and we recorded the arrival time and the arrival amplitude and how many times it bounces off the seafloor. And we figured out for the recorded signal where the direct signal comes from and where the multiple later reflections echoes come from. And at different frequencies, what we did is we used simple intensity of arrival equations to calculate the scattering strength of the seafloor. The scattering strength tells you how strongly the seafloor reflects or absorbs the signal at different frequencies. And we plotted that across different frequencies. We've clipped it up into three equal energy bands, 33% energy distribution, from let's say 500 hertz to 20 kilohertz. And we got figures that look like this. So in different frequency bands, you have the intensity of the energy reflected from the seafloor. And we can combine all those frequencies and we can plot the traces with the GPS information. Now, the objective is to with overlay this information with the local bathymetry profile or local high resolution seafloor profile and figure out and say, because of the characteristics of the reflected signal, the seafloor is mostly rocky or sandy or muddy, so it's safe to deploy here, safe to record here. And so it's basically using the information that's available and sensing the environment. So instead of doing a large expensive survey, we can use the acoustic signals in the environment and tell us about the environment. The same principle could be applied to finding out marine mammals or submarines or mountains or anything. And finally, third example, impact assessment. What impact assessment means is that for any of these industrial noise sources, which are generally very loud, repetitive, happen at regular intervals, there might be temporary loss of hearing or permanent loss of hearing or behavioral change or physical injury to some of the very frequently occurring marine mammals. So the objective is to figure out or estimate that impact safety distances before we can even start the survey. This is a regulatory requirement, and the requirements are probably applicable all around the world, which means wherever you have the survey, you do have to do an impact assessment study, predict the safety zones, tell it to the operator, and then they would define what the safety zones are. So for that, we figure out the characteristics of the source, for example, repetition rate, levels, frequency content, etc. Then we take the environment into account. For example, here we have a study of 3 paths taken by a vessel doing industrial operation in the Brazil basin, and one is deep water and one is shallow water and one is a mixture. And we take the different layers of the seafloor into account, so we figure out how the sound propagates to it. Then for the region, we evaluate what are the target receivers. Basically, there would be 2 or 3 very important target receivers for the region, and we figure out their sensitivity of hearing and physical sensitivity to pressure and other relative studies. And we combine all this and we define safety zones. So in the center, you'll have the noise source and you have distances up to which you can have different impacts. So the important task in this, and sometimes the most difficult task, is figuring out the geology of the seafloor. Most of the times, as I've said at the start, not higher resolution information is available. Now, for example, this is a picture that's extracted from different coring details across the ocean of how the seafloor varies across the earth. Now, this is just the seafloor, not the different layers beneath the seafloor, and which also interact with the sound levels. And as an example here, we have from the study that I've shown you earlier in the Brazil basin, a simulation of how the acoustic signal of 400 hertz propagates through an ocean. And as you can see, it propagates the seafloor and radiates back, and there are multiples. And it's different, obviously, as the frequency changes. So we do studies like this. We figure out what's the loss of acoustic energy, for example, let's say 5 kilometers from the source at 500 meters depth at different frequencies, and then assess the impact zones based on recommendations. So we draw figures like these, which is based mostly on modeling. We draw the safety distances and we report them. That's the bread and butter of our job. So we're almost at the very end. So I do want to leave you with some ideas of what the way this is heading, the way underwater acoustics has heading. In 2019, we've had we had underwater acoustic signal processing challenge from DSTL and Ministry of Defense, and in that they had a pathway for the next 10 or 20 years on what the challenges would be and what engineers should be thinking about indirectly. So for example, you have a poor signal to noise ratio situation in the ocean, which is very frequently occurring. The navigation of autonomous vessels, presence of these autonomous vessels in many multiple autonomous vessels, multiple sensors, integration of those sensors, machine learning, beamforming, etc. So one of the things that we've been working on is a combination of the ideas that were defined here. So on the Autonaut unmanned surface vessel, the idea is to integrate a digital hydrophone array and the thermal camera. And the objective is to focus or beamform the digital hydrophone array in the same direction as the thermal camera is asking you to focus. So for example, if the thermal camera detects a ship far away, we should be able to steer the hydrophone array in that direction. So you have 2 points of information or dual sensory information recording that. Could be the other way around as well. So the acoustic sensor is asking the thermal camera to look in that direction, and the autonomous vessel would go there and figure it out, process the data on board, and display it to the engineer who will make a decision. The reach of these studies is very wide. You have um, you have marine mammal detection, you have applications in defense, for example, border security. You have applications in patrolling. You have applications in safe operations of unmanned surface vessels. And this is been in works for the last 1 year now. And stay tuned. Hopefully, we'll go ahead and be successful with it. Let's see. So that's it. That's my talk. Hope you had fun. Um, I'd like to end with a statement, a conclusion to a statement that I've said at the first. Underwater acoustics is an interdisciplinary field, only in the sense that if you want to divide those fields into individual branches. In the ocean, they are all operating together at the same time. A signal you send interacts with everything at the same time. It interacts with the marine mammal, it interacts with the submarine, the shipping noise is included within it, the chemistry of the water changes its properties, and so on and so forth. So everything's happening at the same time. So all studies are interdisciplinary in nature, at least in underwater acoustics. The way you think about it is, how can you make best decisions, either in a research wise or in a commercial sense? And sometimes maybe, how can you have fun with it? So thank you. That's all. Now I'm ready for questions.